video, we continue chapter 8.5. In this video, we are going to go over the definition of Hermitian matrix. We're going to see how to visually check if a matrix is Hermitian and how to find the eigenvectors for the Hermitian matrix. And then we're going to see something known as the spectral theorem. That's kind of a preview of something you might see if you take a next level complex calculations class. So a real matrix is symmetric when it's equal to its own transpose. In the complex system, a matrix that is equal to its own conjugate transpose is called a Hermitian matrix. And this is after the French mathematician Charles Hermite, who lived from 1822 to 1901. All right, so obviously a matrix has to be square to be equal to its own transpose. So similarly for complex matrices for the conjugate transpose, square matrix A is Hermitian when A equals A conjugate transpose. And as with symmetric matrices, you can recognize a Hermitian matrix by inspection. So to see this, think about this 2x2 matrix, where if you break it down into the components, you'll be able to see really clearly if you've got the conjugates and the transpose equal to the matrix A. So the conjugate transpose of matrix A has this form where the diagonals flip and then every value is conjugated. And so that's just A1 minus A2i in the first entry. The second entry, because the transpose is now C1 minus C2i. The next row, the second row, first entry is now B1 minus B2i. And the last entry is D1 minus D2i. And so if A is Hermitian, then it has to be in this form for a 2x2 matrix, where you've got the diagonals, the same constants, but difference in sign here for the conjugate to change. And then the left diagonals are just A1 and D1 because those have to have only real entries. Otherwise, the conjugates would change. All right, so notice that the main diagonal entries must be real. Similar results can be obtained for Hermitian matrices of order n by n. In other words, the square matrix A is Hermitian if and only if the two conditions below are met. So condition 1, the entries on the main diagonal of A are real. And condition 2, the entry Aij in the ith row in the jth column is the complex conjugate of the entry Ji in the jth row in the ith column. All right, so here's some matrices for us to check to see if they're Hermitian or not. So matrix A is not Hermitian because the main diagonal has an imaginary number here. So the conjugate would be a negative either. Matrix B is symmetric, but is not Hermitian because the entry in the first row, second column, and second column, first row are not complex conjugates of one another. Matrix C is Hermitian, so you can check on the diagonal, you've got all real values. And then if you check the kind of reflections of each entry, 2 minus I in row 1, column 2 is the conjugate of 2 plus I in row 2, column 1. Negative 3I in row 1, column 3 is the conjugate of 3I in row 3, column 1. And then 1 minus I in row 2, column 3 is the conjugate of 1 plus I in row 3, column 2. Matrix D is also Hermitian. That's an easy one because they're all real numbers and it's a symmetric matrix. So all real symmetric matrices are by default Hermitian. They might be less interesting in terms of calculations because there's no complex values, but they meet that definition of being Hermitian. So if A is a Hermitian matrix and its eigenvalues are real numbers, so let lambda be the eigenvalue of, or an eigenvalue of A, and then we're gonna let V be a complex vector of A1 plus B1I through AN plus BNI. So B is the eigenvector corresponding with lambda. So if both sides of the equation, AV equals lambda V, are multiplied by a row vector V conjugate transpose, then V conjugate transpose AV is going to be V conjugate transpose lambda V. You can pull out the lambda, so it's V conjugate transpose V. And so that just works out the lambda multiplied by each component squared and added up. And then furthermore, V conjugate transpose A, V conjugate transposed, we can distribute that through as V conjugate transpose A conjugate transpose V conjugate transpose transpose, because remember the transpose part changes our multiplication when we distribute it through. And so that just simplifies to V conjugate transpose AV. So it follows that V conjugate transpose AV is Hermitian, because after going through those calculations, we ended up right back at the starting matrix. So it's a Hermitian 1-by-1 matrix. And this implies that the single entry, lambda multiplied by each component squared added up, is a real number. So lambda is real. And we did this for a generic eigenvalue. So that tells us that all the eigenvalues of these Hermitian matrices are real. So let's take a look at an example. So here's matrix A. And we are going to find the eigenvalues of this matrix A. So this is the matrix that we already verified by inspection as Hermitian. So we start with the characteristic polynomial lambda I minus A. So that gives us our lambdas minus our diagonal values. And then we factor out the lambda minus 3. So it's like we're going backwards from our determinant calculations here. How we did the row expansion for the determinants, if we factor out the lambda minus 3, and that's multiplied by the determinant of the values that are in not row 1 and not column 1. And then the same thing for the next entry, -2 plus I. These are the determinant values from row 1, columns 2 and column 1, rows 2 and 3. And let's see, this is column 3, rows 2 and 3. And then lastly, if we pick out the 3i, our determinant is the entries in columns 1 and 2 from rows 2 and 3. So this is just a familiar determinant calculation like we did earlier in the semester. And then we can calculate those determinants real easy because they're 2x2s. So we end up with this next calculation here. In terms of our lambdas, we distribute everything through. We end up with this calculation, and we combine like terms, and we end up with this polynomial, lambda cubed minus 3 lambda squared minus 16 lambda minus 12. That's factorable. So that's our characteristic equation. We set it equal to 0, and the eigenvalues are all real numbers that satisfy this: -1, +6, and -2. So now we want to find the eigenvalues. So to find the eigenvectors, oh, sorry, this should say finding the eigenvectors. We found the eigenvalues in the previous slide. So to find the eigenvectors of the complex matrix, we're going to use a procedure similar to what we used for the real matrix. So for instance, in the previous example, to find eigenvectors corresponding to the eigenvalue lambda is -1 that we found, you just put lambda equals -1 to this equation, the characteristic matrix multiplied by vector v1, v2, v3 set equal to 0. So if we put -1 in here, we can solve this equation here to get v1 is -1, 1 plus 2i and 1. v2 is these 3 values, and v3 are these 3 values. So these are the eigenvectors corresponding to lambda 2 equals 6 right here for v2, and lambda 3 equals -2 corresponds with vector v3 here. Okay, so to find the eigenvectors, you plug in the different lambdas into the equations and solve. All right, our last theorem is a well-known theorem known as the spectral theorem. We're not going to do the proof. You can go look it up online or in a textbook. You may see this in physics. That's one reason I wanted to make sure we cover it. So what the spectral theorem, or theorem 8.11, says, if A is n by n Hermitian matrix, then the eigenvectors corresponding to the distinct eigenvalues are orthogonal, and then A is unitarily diagonalizable. All right, so down here we've got the first part of the proof. The second part of the proof you can look up online or try to work through on your own if you're feeling ambitious. So to prove part 1, we let v1 and v2 be 2 eigenvectors corresponding to the distinct and real eigenvalues lambda 1 and lambda 2. We know that AV1 equals lambda 1 V1 and AV2 equals lambda 2 V2. So we get these equations that are shown below for the matrix product, AV1 conjugate transpose multiplied by V2. So we can see that first product works out to be lambda 2 multiplied by V1 conjugate transpose multiplied by V2. And the second product, if we do it in terms of substituting in the lambda 1, not the lambda 2, we get lambda 1 V1 transpose V2. So we have here now lambda 2 V1 conjugate V2 minus lambda 1 V conjugate V2 is 0. So that just tells us lambda 1 minus lambda 2 quantity multiplied by V1 conjugate transpose multiplied by V2 is 0. So we know lambda 1 minus lambda 2 is not 0 because lambda 1 and lambda 2 are distinct real eigenvalues. So that tells us this relationship V1 conjugate transpose multiplied by V2 is 0. So this shows the orthogonality. So vectors, eigenvectors V1 and V2 are orthogonal. So part 2, you can Google the spectral theorem to see the proof, or check another textbook. So in the group problems, you're going to do some calculations with unitary and Hermitian matrices, and in your lab assignment as well this week.